All right. I hope you can see my screen and everything is fine.
Yeah.
All right, sure. So I can begin. So I am Akrash Sharma. My name is Akrash Sharma, and I am a fourth year honors computing science student at the University of Alberta. As for my past work experience, I've been a research assistant. I currently am at the Wishart Lab. I've been a teaching assistant for some computer science courses at UFA, and I've been a data science intern in my past summer. As for my hobbies, I really like playing badminton. So if anyone wants to play badminton, feel free to let me know, and I'll definitely be down to play badminton. And I'm really interested in AI, artificial intelligence, which is a booming field at the moment. It comprises of many different sub-branches: ML, NLP, computer vision, reinforcement learning, etc., etc. So today I'll be talking about a project that I did in a research project that I did in one of my courses. The course is called AI Capstone. It's offered at the UFA, and we work as a group to do a research project from scratch. And the professor is Dr. Russ Grainer, and our supervisors for this project were Dr. Brian and Dr. Kyle. I worked along with 3 other teammates in this project. And the name of the project is Large Vessel Occlusion Prediction. So today I'll be addressing what the problem is, why the problem was important and non-trivial, how we addressed the task, the evaluation and the results we achieved, and what we learned overall from the project. So to begin with, what is the problem being addressed? Large vessel occlusion. So we all probably know what stroke is, and the most common type of stroke is called ischemic stroke, which is when there's a blockage in one of the vessels supplying blood to the brain. And when this vessel is a large artery, a large blood vessel, then it's called a large vessel occlusion. As you can see in the diagram, a blocked artery, which is a large blood vessel. And as for the data set, we were provided with various different data sets for different patients, which comprised of EEG data, accelerometer data, gyroscope data, some basic clinical data, and our output variable, which we wanted to predict LVO. So the goal, or the overarching goal of the project, was to use a machine learning model to learn all the patterns in the data, learn the trends, and then we build a classifier such that when you give the measurements of a new patient, we can output whether the patient is likely to get an LVO and how likely he or she is to get an LVO, like in terms of percentages. And we also have a custom evaluation metric, which is a loss function, which I'll get to later. So to begin with, what is EEG in the first place? EEG is basically capturing the electrical activity in the brain. And the brain waves can be comprised of 4 main channels, which we can see on the screen: AF7, AF8, TP9, and TP10. So we have this headset called a Muse headset, which can measure all the electrical activity in the brain when you wear it. I actually have it right now. I'm not sure if you can see it. So this is how you wear it, something like this. And when you wear it, you can essentially think of it as a headphone, which you can connect to your laptop. But this way, you're connecting to a particular software that is reading all the measurements. And after you read all the measurements, the data is divided into 5 main signals, depending on the frequency bands. And they have different names: gamma, beta, alpha, theta, and delta. And it's a very quick procedure. So it's just a 30-second recording, and you're done with it. And it's a simple instrument. Next, after measuring the EEG data and some of the clinical data, what situation will this model or this problem be used in? So this potential use case is that if we have a patient who potentially has a stroke or some sort of problem and is arrived at an ambulance, in that situation, the paramedic has to quickly assess whether there's a possibility of a stroke or a large vessel occlusion and transport the patient to a nearby facility or a facility accordingly. So to do this, normally the paramedics usually have different approaches, and they have different methods of assessing whether there's a likelihood of LVO, which is the LAMB score, which I'll get to in a few moments. But using our models and using latest EEG techniques, you can just use this simple Muse headset, get a 30-second recording, and get some few clinical measurements like the height, age, and the gender. Just input that into the model, and the model will tell you the likelihood of LVO and the expected loss. And that way the paramedic can decide which hospital to appropriately transport the patient to. So next up is why this problem was important at the moment and why it's not trivial. It's an open research question, and we built on previous researches, since many different research has been done on predicting whether someone has a stroke or not. But most of the research either use clinical data, like a lot of clinical data, or they use only EEG data to predict whether they have a stroke or not. However, our research was unique in the sense that we are only using limited clinical data that's available on site in the ambulance, basically weight, age, gender, and that 30-second recording, so that we have a quick method of assessing whether the person potentially has a large vessel occlusion or not. And next, we're working with EEG data, which is quite noisy. The data was really noisy. As you can see, it's just brain waves, so there's a lot of noise in the data. And we're combining it with clinical data, trying to figure out how to use the maximum potential of both data sets and predicting, essentially. So the current method, as I mentioned, is a LAMS technique. This is what the paramedics use currently to assess if someone has a stroke or a large vessel occlusion rather, or not. It's a few measurements that the paramedic does, like they observe the facial droop, whether the face looks normal, and they assign a score between 0 and 1. Similarly, for the other 0 to 2, they assign a score. Arm drift, they tell you to keep doing this, something like this. Oh yeah, actually something like this. Oh yeah, opposite direction. Opposite direction. And the last thing they measure is the grip strength. They assign scores based on their qualitative assessment, and they add the score. If it's greater than 4, there's a high likelihood that you possibly have LVO. And as you can see, it's not a very robust technique, but it has proven to be about 70% accurate in most cases. So now our task, how we approached it once we have the data sets. As usual, in all of data science projects, the first part of the project is data preprocessing, cleaning, feature extraction, etc. So for the clinical data, it was simple. Just load the clinical data, do some basic cleaning, and select the features that are available on site. Since the dataset we were provided was extremely huge, we only selected those features that we think the paramedics can get on site: the age, the LAMB score, the height, weight, etc. And we calculated something called the time elapsed, which is just the time in minutes between when you start recording the EEG and the time if the person gets a stroke in the ambulance. Next, for the EEG data, we had 2 different techniques of feature extraction. And since EEG data is quite noisy and it's in high dimension, we have to perform something called dimensionality reduction, which is essentially just reducing the data set into projecting it to a smaller space, and feature extraction, of course, because we want the most important features to be part of our model, not just giving everything to the model. And as for the techniques, I can give a high-level overview. So for HFD and DFA, it's a promising technique that has been used in analysis of Alzheimer's. So we decided to choose this as well to see how well it does on EEG data sets in pre-processing it. And for this one, we just have to calculate 2 values called HFD and DFA, which are short for Higuchi fractal dimension and detrended fluctuation. So There's essentially a way of calculating this using libraries and predefined methods. You calculate the values for each of the 4 channels that the Muse headset read, and you get some values, and we use that as our pre. Or that was one of the simple methods. And the other method that we used was quite a popular and standard method that's used in preprocessing. It's called the wavelet transform. So the idea for wavelet transform is just that we have 4 different channels, as I've mentioned, and I'll keep mentioning throughout the presentation. So for all these 4 channels, we can have 5 waves for each one of them. The waves that I mentioned before, gamma, theta, delta, beta, etc. So 5 waves, 4 channels. So in total, we have 20, 5 times 4, 20 values. So for each of these 20 values, we calculate something called the Shannon entropy and the energy of the waves. And we get another bunch of real values, real scalar values based on that. And in this way, we have reduced the dimensionality of the data set, because essentially it was 5,000 times 4, which was 20,000 different values, 5,000 rows, 50,000, sorry, times 4, 200,000 different values. And now we've reduced it, shrunk the data set by calculating 2 values for each of the four of them. So that's the basic idea of dimensionality reduction in this sense, which wavelet transform was performing. And we get more significant and important values which are used as features for our machine learning model. So that was all about the data preprocessing. Now, finally, we can come to the models themselves. As for the models, the first approach is to start from traditional basic machine learning models. However, we had 2 entirely different data sets. Clinical data, which is just basically, as I mentioned before, weight, age, gender, whereas EEG data is a bunch of weights. But now after preprocessing, it's a bunch of scalar values, but they're entirely different data sets. So the first approach that I had was, let's just make a model for each data set so that the model can specifically learn the trends in each model can learn the specific trends in each data set. And then we combine the models, and then we get our final prediction. That was my initial approach to the task. And the details in between are just a great search CV is basically just finding the best hyperparameters for the best parameters for the model, and you get a prediction, accuracy, and our evaluation metric. Now, how did I quote unquote combine the models? So there are 2 techniques for combining models. The idea is very simple. You have your data set. You can have a bunch of different models, machine learning models. You train the models, get your output for stacking classifier. Yep, there we go. For stacking classifier, you essentially have all the models, you get your outputs. So like, let's say this model predicts that the person has a stroke. This one, an LVO, this one predicts he does not have. So 0, 1, the output will be 0 to 1 binary, has an LVO, does not have an LVO. So each model is predicting something after learning from the data set. Then all those predictions are used as a new data set. So they're used as new features for your meta learner. And the meta learner, since it's just using simple features as 0 and 1, we tend to use logistic regression for this. So we also use logistic regression since it's a simple method, simple machine learning technique. And then you get your final output from the meta learner. So it's a very simple idea. Different machine learning models, they learn, they're trained, they learn, they give their predictions. Then those predictions are used as new features for a new machine learning model, which then assesses the overall weight of them and gives them final prediction. And that's the idea of stacking classifier. Voting classifier is somewhat similar, and there are 2 different types again, hard voting and soft voting. So for hard voting, in voting classifier, instead of having another meta learner, instead of having another model, we just get the average ourselves. So we skip the step of the meta learner essentially. So if the machine learning models, they predict 1, 1, 0, if this one predicts that 1, oh, the person has an LVO. Machine learning model 2 says, yes, he has an LVO. Machine learning model 3 says, nope, 0, the person does not have an LVO. Then we just take the majority vote, and that wins 1. That's hard voting, take the majority vote. Simple idea. As for soft voting, it's similar except use percentages instead of just the fixed true values, because the models can also give the probability of how likely the person has an LVO, how likely the model thinks that the person has an LVO. So say this model thinks that 80% sure that, yeah, this person probably has an LVO. This one says 90%, 20%. Take the average and then give the decision based on that. So these are two techniques that we use to combine the models. And I'll get to the results at the end. But after using those techniques, we also tried the other way, which is the normal way. Just combine the data sets instead of building two different models. Combine the data sets, even though they are extremely different data sets, but the patients are the same. So just combine the two data sets, clinical data, EEG data, used one model, get the best parameters, do something called k-fold cross-validation, just to ensure that our results are robust and reliable, rather. And you get your prediction, accuracy, and evaluation metric. So for this, we used a bunch of different machine learning models, SVM, it's called support vector machine, and we use Gaussian process. And I particularly tried different kernels. They are kind of like functions. So there's they can be linear kernel, exponential kernel. A linear essentially just a line separating the data. Exponential will be an exponential function separating the data, etc., etc. There's some projection to subspaces and all, but you can think of it in simple ways as just functions trying to separate the data. So we tried a bunch of different kernels as well for each of the methods that we had. We also had another method called random forest. Similarly, a bunch of different kernels, get the best parameters, get our prediction. And lastly, we also tried deep learning and recurrent neural network techniques. So similarly, combine both data sets, and we had EEGNet, which is a custom convolutional neural network, which has been designed specifically for EEG data. So this was a promising technique, a powerful technique, customly specifically geared to EEG. So we use that as well. And LSTM, which is being used quite a lot at the Wishart lab as well. And we get our predictions. Now, finally, how did we evaluate our results before I get to the actual results? So of course, we definitely use accuracy to gauge how accurate our models are. However, our domain experts wanted to penalize the false negative more. So the idea was that you want to punish the model more if it makes a mistake predicting that the person does not have an LVO, when in reality the person has an LVO. So that's a big mistake that we don't want the model to do, because if the person has the disease, they need to be transported to the hospital. So we don't want the model to make such mistakes. So that's why there's a 4 on the false negative, to penalize that more and punish the model when it makes such type of mistakes, so they can make those mistakes less often, less frequently. So we designed this after a bit of a discussion with the domain expert. And finally, we can come to the results. As for the results, as you can see, this is the expected loss. So we want to minimize the loss. And clearly LSTM and EEGNet had the lowest loss, the neural network techniques. However, as we can see, there are two different bars, blue and red. So we tried on the clinical data only versus we experimented what happens after adding the EEG data, whether EEG is valuable or it's just random noise that we don't need. And most of the models tend to have a worse performance with the EEG after adding the EEG data. The loss increases, except for SVM and EEGNet. Those are the only two models for which EEG data turned out to be beneficial. And as I mentioned before, we were doing the dimensionality reduction from 20,000 to 5,000 or to 40 rather. We tried experimenting with different time points as well. What if we just provide the whole data set, like all the 20,000 points to the neural network techniques, LSTM and EGNet, what would happen? And what if we just provide like 5,000 time points after doing the dimensionality reduction? And as we expected, the 5,000 time points is better for both of them. So dimensionality reduction was helpful essentially because we're providing the most useful features. And unfortunately, the fancy technique of combining two different machine learning models, trying to do that, it had a worse performance than just combining the data set. That's also one thing that we observed. And that was in terms of the loss function that we created. However, in terms of accuracy, it's almost the same results. The support vector machine, the SVM technique, had the highest prediction accuracy, 81% with both of the data sets. And the others were also around in the 70s, which is not that bad. Overall, at least we were able to achieve a higher accuracy and more stable and robust methods than the LAM score itself, which is measuring the hand movements, the grip strength, which is said to be around 70% accurate. And what did we learn from this? So while we were doing the experiments, while we were running the experiments, as I mentioned, we had two different feature extraction techniques. So we saw that some of the techniques are good for some models, whilst one of the techniques is good for another model. HFD and DFT were really good for the neural network techniques. However, wavelet was much better for the SVM support vector machine. Those are our observations. And another key observation was that standardizing the data set is really important, which I'm pretty sure all data scientists do by now, but it's really important as we observed a significant effect in the accuracy if we do not standardize the EEG data set, even after preprocessing and after doing the feature extraction. And lastly, as I showed the graphs, increasing the time points makes the model overfit. So dimensionality reduction is also extremely crucial in these tasks. And a few more insights was that neural network techniques had the highest performance in terms of expected loss. However, SVM had the highest performance in terms of accuracy. We also noticed that LSTM does not necessarily perform better after adding the EEG data set. The EEG data seems like LSTM was not doing well with EEG data, probably because it's too noisy for the model to handle, or maybe more hyperparameter tuning needed. But that's one observation that we made. And another observation, which I mentioned in showing the graphs, the combination of models can perform worse than just a single model. But experimenting and finding out is part of the research and seeing which method works and finding the best results. And lastly, while we were doing those, while we were running those machine learning models, as I mentioned, we were trying different kernels, function spaces is what I would like to call them. As I mentioned, linear, exponential. Yes, there are many others that we tried. RBF kernel. We noticed that all the machine learning model techniques that we had actually performed the best with linear kernel. So the conclusion one can make from that is that after doing all the pre-processing, the wavelet transform, or after reducing the data set, essentially doing the dimensionality reduction, the data set is linearly separable. You can separate it by a line, essentially. That's what the conclusion would be, since SVM and Gaussian process has the best performance with just a linear kernel. So you can make the decision with just a linear kernel, whether a person has LVO or not. And extra things that we left to consider in the future that we weren't able to get to would definitely be interpretation. There's a technique called GradCam, which we were touching at in the end for the EEG data. We essentially want to see which particular wave frequencies have higher importance, like are contributing the most to the model. So interpretation is a key step after building the machine learning models to see which frequencies are doing are contributing most to the model, and sharp values for the clinical data to see whether particular genders have a higher likelihood of getting LVO, or particular weight ranges have a higher likelihood, stuff like that. So interpretation of the model results, essentially. And the next thing to do would also be to add the gyroscope and the accelerometer data, which we didn't get to in our research because gathering that data is a bit more work, which we're not sure if the paramedics do that in ambulances. So we were focusing on what they can do in an ambulance and get done in like 30 seconds to 1 minute and assess whether the person has a large partial occlusion. But that is also something that you can definitely look at, that the supervisors, we opened it to them that they can definitely add those data and see if there's an improvement or how those data sets also affect the study. And lastly, as usual, hyperparameter tuning, just fine tune the models, see if there's more tuning that if you can make the models better and increase the accuracy, etc. And that brings me to the end of the presentation. Thank you.